So we've talked about conduction and convection and R value. So the last thing we need to talk about is radiation. Radiation is perfect to talk about this time of year because it is December when I'm recording this right now, and it's cold, like 0 degrees. So why is that a perfect time to talk about radiation? Because most of you get in your cars, and on a sunny day, on a cold day like this, you still feel heat. You still feel warmth from the sun, and that's because of radiation. Radiation is the process by which energy is transmitted through a medium, including empty space, as electromagnetic waves. And for the purpose of this class, the only thing we're really going to look at for radiation is this law, Stefan's law, which talks about objects gaining and losing thermal energy by electromagnetic radiation, and that is represented mathematically using the equation P net equals Stefan's law, or Stefan's constant, which is the sigma symbol there, times area. Let me highlight them for you. Stefan's constant times area times emissivity times change in temperature. But it's a little bit different this time around because our change in temperature is temperature to the fourth, and it's also in Kelvin. How do we know that? Stefan's constant down here, this sigma is always going to be 5.6696 times 10 to the minus 8th, and the units for that are watts divided by meter squared times Kelvin to the fourth. So you know that you have to be meter squared, you have to be in Kelvin to the fourth. The other thing that you need to know is watts right here. Watts is still a value of joules per second. Why is that important? Not very good writing. Why is that important? Because this is a power equation, and often we're going to want to know the energy transfer Q. And Q is going to be power. Q is still power times change in time for us. Let me write that there so you see it. Okay. We're still going to need to find Q. So we need to know that watts is joules per second, so that our time will always have to be in seconds when we're doing stuff. Okay, let's use that as an example. Oh, sorry. E is the emissivity constant. Emissivity constant will be a different number for each material that you're talking about, and then T is temperature in Kelvin. So example, prior to dressing for school, a student watches the morning weather to decide what clothes to wear. A lot of my students also need to start watching the morning weather to decide what clothes to wear because it's cold and you're wearing gym shorts and t-shirts. I digress. The bedroom is 65 degrees Fahrenheit and the student's skin is 91.4 degrees Fahrenheit. Not sure why they use Fahrenheit because they make us convert, but that's okay. We can do that. Determine the net energy transfer from the student's body during the 15 minutes. Again, notice this is minutes. We're going to want seconds, so keep that in mind. Spent watching the morning weather. Note, skin emissivity is 0.9. Surface area of the student is 1.3 meters squared. Perfect. Those are easy units to use. Known values. Area, 1.3 meters squared. Emissivity constant is 0.9. That's the letter E. Stefan's constant always is that sigma, and it's always that same number, 5.6696 times 10 to the minus 8th. Bedroom temperature, 65 degrees Fahrenheit. Temperature 2, skin temperature is 91.4 degrees Fahrenheit. You could convert now if you would like, or you can do it later. In the example, I'll do it later, so we'll just move on. And then the change in time is 15 minutes, which right off the bat, again, we should convert that to seconds because we need watts, once again, is joules per second. And I'm still not good at writing with my mouse, but that's okay. Okay. All unknown values. I'm not sure why they have that at the bottom right away, but that's fine. We don't know P, we don't know Q. Keep in mind we're going to be solving for P with the equation we have and then solving for Q afterwards. So our equations will be P net and Q equals P times delta T. How do we use our known values? We use T. They're going to start by solving for T to the fourth minus T to the fourth. They converted our 65 and 91 point, whatever it was, I don't remember right offhand, to Kelvin. Oh, there they are, 91.4 and 65. They converted those directly to Kelvin. If you don't have that conversion easily in front of you, You can use the conversion factors and conversion charts to go from Fahrenheit to Celsius and then Celsius to Kelvin. When they do that, they take 306.15. Make sure you're doing this in proper order. So you have to take this to the fourth and then do this to the fourth, and then you subtract those two big numbers. And when you do that, you end up with a large number. 1.567 times 10 to the 9th Kelvin to the 4th. So then you take that, and it's as simple as plugging in. So you have Stefan's constant, which why don't we highlight what all of these numbers are. So I've got this number here, matches up with Stefan's constant right here. This number here matches up with my area that I was given. This number here, sorry, that makes it hard to see. Let's go with this number here, matches up with my emissivity, and then this number here matches up with my change in temperature. Okay, so they multiplied all those together, and we got 103.92 watts. So I'm done. No, I'm not done, because that is P net. I need to now find Q. How do I do that? Q is P times delta T. I just found P, my delta T, my delta little t, that I should say was time, 900 seconds, so I just multiply those together, and now I'm done. 93,500. I assume that's a rounded number. I would keep it as more of an exact number, but that's what they like to do on these examples, and so that's what they write. Alright, so there is radiation. We now have examples for all different types of energy transfer and should be able to do all of our practice problems. Good luck.